Welcome again to the ISGAN webinar of today. This is Untitled from Virtual Learning. Before leaving the floor to the speakers, I will introduce the webinar of today. This is titled Modeling and Control of Renewable Energy Power Plants for participation in a dynamic virtual power plant, also called DVPP. This webinar is hosted by ISGAN. ISGAN is the short name for the International Smart Grid Action Network. Okay. ISGAN is a technology collaboration program of the International Energy Agency, but also an initiative of the Clean Energy Ministerial, formally established in 2011. ISGAN creates a strategic platform to support high-level government attention and action for the accelerated development and deployment of smarter and cleaner electricity grids. ISGAN consists of 27 contracting parties from all over the world, represented in 6 working groups that cover the different smart grid topics from cost-benefit analysis to flexibility markets. ISGAN's vision is to accelerate progress on key aspects of smart grid policy, technology, and investment through voluntary participation by governments in projects and programs. ISGAN activities focus on 5 principal areas, such as policy standards and regulation, finance and business models, technology system development, workforce skills and knowledge, users and consumer engagement. ISGAN facilitates dynamic knowledge sharing, technical assistance, peer review, and project coordination among its contracting parties. The ISGAN value proposition relies on conferences and workshops, policy and technology briefs, discussion and technical papers, casebooks, and webinars. Within ISGAN, Virtual Learning offers to the ISGAN community means of rational and continuous technical skill complement and update in the field of smart grids. The Academy is proposed as a set of e-learning reading core modules dealing with the entire value chain of smart grids. The webinar of today, Modeling and Control of Renewable Energy Power Plants for Participating in a Dynamic Virtual Power Plant, presents models and local control schemes for integrating renewable energy resources in DVPPs. This includes wind turbines, wind farms, PV system, biogas, hydropower, and solar and thermal. The generating units are described in a unified model for local control design, simulation, and the analysis of their dynamics. The models are intended for the integration into a high-level control design. The speakers of today are from HTW Berlin and are Stephan Kusche, Florian Pöschke, and Horst Schulte. I'm sorry if I pronounce them bad, but they can present themselves, so you can hear from them the proper way. So now I leave the floor to the speaker. Please use the question and answer tool to pose the questions to the speakers, and we will have a question and answer session at the end of the session. And the recordings, as usual, will be available through the ISGAN YouTube channel. Now, please, I leave the floor to Horst. I will stop sharing my screen. Okay.
Okay.
The webinar.
Okay, thank you for nice introduction. So I start, and then my co-workers will follow. So I'm Horst Schulte from the University of Applied Science here in Berlin. So first of all, I'll give you a short introduction, what is the objective and the key questions which we have to consider in our research project. Then I give you primary, secondary RPP models, and step by step, my colleagues give you a detailed description of wind turbine, wind farm, and PV. And then I go back to a more broader view and give you the link to the higher level control by transfer functions. So first of all, as I've mentioned, that is our main scheme of our project. So our task in the project is to consider and to derive generic models of DVP system. So DVP means a dynamic virtual power plant. So in this, we focus on the dynamics. That means we have also taken into account the dynamics of the devices. So we focus here on 3 different types of devices. The first type is a synchron generator-based systems, solar, thermal, biogas, and hydro. Then we distinguish between a full converter and a rotor side or a partial converter. That's particular in the wind turbine important. So in wind turbines, they have full converter and rotor side converter. And last but not least, we also considered photovoltaic power plant. So what we have actually, as mentioned before, we have different types of power plants, wind turbines, wind farms, PV systems, biogas, hydropower, and so on. That is very important because here we describe all these different types of technology, one by unified model structure. That means we have a unified interface between the higher level and the lower level control. So we have some embedded local controllers, which I give you here some example how we have tuned this, on which model we have considered and designed. Then I give you later an integration of this different models into higher level things. So here are the 4 important questions which we have addressed. So first question is, which RPP dynamics are important? RPP stands for renewable power plant. So which dynamics is important and which is important for higher level design? Then the first question is which functionality we need, which is necessary for the design of a DVPP, which kind of model structure can we use, so which are suitable for the dynamic representation, to represent dynamics, and also to take into account the needs of a control design. That means, are this suitable for a model-based design? So we have 2 different tasks: model-based design for a local controller and also higher level controller design. So we give you here some internal how we have to deal with these problems in our project. So first of all, so I'm not sure how it's familiar with this, but it comes more or less here. We can start with a textbook. So normally you can derive and describe nonlinear systems, or more precise, first linear systems by state space models. And we combine state space models by weighting combination of this into a nonlinear system. And the advantages of this, we can address both. We can address the frequency domain by local models, but we can also describe the EMT model behavior. So we have differential equations too. So that's the main method we use. Now I come to the requirements for the modeling. So our models need a reference input, which comes from the DVPP level for the devices. The devices depends on the applied control scheme. So that means we have not just the physics of the system, we have also the control scheme, which is in the closed loop. And this is, of course, important. We have a closed loop system. So we have a strong dependency between the physical model and the controller in a closed loop. You see this on the scheme. So we have here to distinguish for each of the devices between 2 main tasks, 2 main submodels. The primary power, that means the physics to transform the renewable energy sources, wind, measured by effective wind speed, and we also, for the PV, the radiation. We convert this into a DC power, and based on the DC power, we're able to convert this in a way which fits here to the grid. So we distinguish between 2 different kinds of converters, grid following, grid forming. So in total, we have here power plant control, which interacts both with the primary and the secondary power converter, and we have the external link to the higher level dynamic virtual power plant. And of course, this is the connection to the grid. We will feed the grid, inject the grid by power and distinguish between reactive active power. Feedback is the voltage terminal on the DVPP level, and this is on the local level. So now I switch to the next task.
Yeah. So this is where I take over. I'm Florian, and I will present the primary converter of the wind turbine at this point. So first of all, the objective for the modeling was there to provide a process for the derivation of wind turbine models that are suitable for both control design and simulation studies. Of course, there exist different types and designs of wind turbines. And in this case, we considered a three-level bladed horizontal axis wind turbine with a power rating of 5 megawatts and a type 4 wind turbine that is connected by a back-to-back converter to the synchronous generator on the wind turbine side, as shown here. So for our wind turbine modeling, the main power dynamics are determined by the rotation that is influenced by the nonlinear aerodynamics. That is the reason we use the TS modeling technique Horst described earlier to model the aerodynamics, the drivetrain, and the mechanical modeling. While the mechanical modeling has little influence on the electrical grid, we still included this in our models in order to be able to evaluate the loading that would result in certain scenarios where the turbine is operated in. As a renewable energy source, we use turbulent wind fields that can be generated according to different characteristics like turbulence intensity, and then calculate an effective wind speed that is fed into the wind turbine. For the controller, we derived a controller that is capable of operating the turbine in a large operating range, which will be discussed in a second, and it is based on an observer that reconstructs the wind speed, and this is important for monitoring and estimation of the available power, also for the control scheme. The generator is usually just depicted as a simple transfer function due to the decoupling of the mechanical side and the electrical grid by the back-to-back converter in type 4 wind turbines. So what we did here was we used FAST, which is an aeroelastic simulator, as the foundation for our modeling. This aeroelastic simulator is suitable for certification of wind turbines and is used in the industry for load evaluation. It inherits different degrees of freedom, like aerodynamics, towers, blades, drivetrains, or even platform in case of offshore wind turbines. It doesn't have any electrical connection, but it has a modular approach to parameterize the individual turbine components. And then we use the built-in linearization functionality to derive the partial derivatives or Jacobians, and then integrate this into a TS model as shown here. So when we have the FAST model, we perform a trimming analysis to find out about the steady-state input values that would result in steady-state behavior of the turbine in our operating points of interest, then use the linearization and then build up this model. For example, we can see in this plot the pitch angle and the generator torque at different wind speeds and power operating points that would result in steady-state behavior of the turbine. Afterwards, we can simply build up a TS model for the entire turbine. So in this case, we decided to include the tower side-to-side motion that is shown here, the tower fore-aft motion represented by those states, and the drivetrain motion that is represented by those states, and integrate this into a TS description as given by Horst. Therein, the wind speed is a premise variable of our TS description, and the wind speed is actually also treated as a disturbance to the system, as shown here. And the state space matrices that are used are gained by the linearization procedure. So for example, here in the upper plot on the left-hand side, we can see the sensitivity to changes in the pitch angle of the rotation on the left-hand side, on the right-hand side of the tower fore-aft movement. And this clearly implies the nonlinear behavior that we are facing with the wind turbine. So then we can then we validated those models against the original fast model within a power tracking scenario. So we demanded the turbine to be operated with different power levels that is following some reference. And without going into much detail, what we can see is the fast model and the TS model actually fit very well for all of the considered aspects. That is the power, the rotational speed of the turbine, the torsional drivetrain angle, the tower top displacement side to side, and the tower top displacement fore-aft direction as shown here. This leads us to the conclusion that the TS model provides valuable description for integration into simulation studies, as it gives us the possibility to predict how the turbine will behave. So then there's a problem remaining, and that is the wind speed is usually unmeasurable for control purposes. So we've seen this equation before, where the wind speed is treated as a disturbance to the system. And the solution for that can be to augment our original system description to include the wind speed as a state of the system, which gives us this augmented system description here, using the previously derived disturbance input gains, BDI, within this description. And then we design an observer for this augmented system that allows us to reconstruct or estimate our current effective wind speed. So in this slide, we just have a quick look at the performance of the wind speed observer. So what we see in this plot here is in black, one hop height component of the turbulent wind field, while in yellow and green, the reconstruction from the wind speed observer is shown. What we can see is that it gives us very suitable description of the current effective wind speed that can be used within the control scheme. And further, the wind speed observer allows for the implementation of condition monitoring systems, so-called digital twins. Also, the estimation of the available power. So when the power is not at its maximum, we can still use this reconstructed wind speed to identify the maximum possible power that can be extracted from the wind turbine. And possibly we can enhance an optimized wind farm operation in terms of load balancing, or even maybe increasing the energy yield in total. But this is still subject to research and needs to be further investigated. So whenever we want to perform power tracking operation, because the DVPP would command desired power level of the wind turbine, we're facing a problem at the wind turbine level. If we look at this formula here, this tells us that the power of the wind turbine is dependent on the current wind speed and also on this power coefficient, and depending on the tip speed ratio and the pitch angle as shown here. What we can see from here is there are many operating points that share the same value of the power coefficient. So it's not unique. That is not unique where the turbine needs to be operated at which operating point. And this is actually a question of choice. So the question we were answering ourselves was, what are the different dynamical properties of different strategies? And for that reason, we investigated two different strategies, where the first strategy, so operating strategy 1, relies on a variation of torque only when we want to achieve the desired power level from the higher level control scheme. That is, we keep the rotational speed constant, but vary the torque depending on the demand. On the other hand, in operating strategy 2, we're exhibiting a variation of both the generator torque and the rotational speed to match the desired power level as shown here. For a maximum power point tracking operation, which is the usual way the turbine is operated, both operating strategies actually share the same operating points. However, we can see that depending on the power level, we are operating on quite distinct different operating points on this power coefficient surface. If we look at some results, we can see on the bottom here, we're operating the turbine at turbulent wind field with a desired power level of 70%. And what we can see is both strategies have almost the same power output. However, as shown in green here, in operating strategy 1, the rotational speed is kept at its nominal value, while in operating strategy 2, the rotational speed is considerably reduced. Due to the fact that we incorporated those both strategies in the TS framework and controller of the TS framework, it is also possible to blend among the two operating strategies. And this is done in the purple lines. So we blended from operating strategy 1 to operating strategy 2 within 15 seconds and then back. This results in a slight exceedance of the power level due to the deceleration, or in a decrease of the power level due to the acceleration of the turbine whenever this is processed. So now the question is, how is the power tracking or how are the different strategies affecting the power tracking dynamics that are attainable? So for that, we operated the turbine at constant wind speeds and demanded the turbine to vary its power output in a step change way, and for different magnitudes of the step change and different wind speeds. And what we can see is if we only use the generator torque in operating strategy 1, we actually get a quite uniform behavior for all considered operating points. And this shows this can be easily represented by a simple transfer function of first order, where the power tracking dynamics is mainly determined by the generator dynamics applied. However, in the second operating strategy, due to the variation of the rotational speed, the inertia plays a bigger role, and we can see that depending on the power operating points, we have quite different trajectories shown here. And depending really on the power operating point and current wind speed, the response of the wind turbine is quite different. And therefore, we need a more complex transfer function to describe this behavior, where we suggest using this structure here with appropriate parameters to envelope our lower and an upper bound into this behavior. So in operating strategy 2, the power tracking is a combination of the generator and rotational dynamics that are governing this, this behavior here. So now I talked about the primary converter side of the wind turbine, and I will also introduce you to the secondary converter side that Horst mentioned earlier, and this will also apply for the PV system that Stephan will present in a second. So for the secondary side, as mentioned, we use a back-to-back converter to connect the turbine to the electrical grid, and there we included the DC link dynamics, and the main dynamics that govern this converter are the control schemes within. So the goal is to set this terminal voltage E that is shown here to be injecting the power levels that are desired. So therefore, we consider two different schemes. And the first one is the commonly used grid following scheme that relies on the use of a phase lock loop, as shown here. So this is a simple power control cascaded with an underlying current controller, and where we use the measurement of the current and the voltage at the point of common coupling to calculate the powers. And then this complex power controller here generates a reference current that is processed by an underlying current control scheme in a rotating reference frame. And then we rotate this back to stationary frame and obtain our terminal voltage that is used as an output of the back-to-back converter. On the other hand, we also included a grid forming scheme. And the main idea in this grid forming scheme is to use groups on both the reactive power and the active power, where the reactive power group that is shown here actually sets a voltage magnitude at the point at the terminal voltage, and the active power group sets the rotational the angular frequency of this reference voltage for the terminal voltage, and then together they form a reference voltage at the terminal, and together with a measurement of the voltage at the point of common coupling and the parameters of the filter and the transformator, we can algebraically relate those two voltages to actually again obtain reference currents, and those reference currents are then processed by an underlying PI control scheme for the current that then sets the real applied terminal voltage. It should be noted that this current controller is also operating in a rotating reference frame, however, not in a frame that is obtained by a phase lock loop, but the reference frame is directly established by the droops of our active power control. So we use the same angular frequency for this rotating reference frame, and therefore we don't need a phase lock loop. Okay, this was the short introduction to the wind turbine and the secondary conversion. And now Stephan will follow with the PV generator side.
Okay, hello to everyone. In the following slides, I want to give a short overview about the PV power plant generation and the model we implemented for this. On this scheme, we see an overall overview. We have here the primary conversion on the right-hand side and the secondary conversion Florian mentioned before on the left-hand side. On the right side, we start with the irradiation S, which is fed into the electrical model. And we also have a temperature model, which is, but in this presentation is neglected because in the time range we usually simulate, the temperature change is not that much, so we can ignore it. So essentially, the PV module consists of the electrical model. This electrical model is connected to the DC link via the converter, the DC-DC converter. And therefore, we have a converter model, which is controlled via the duty cycle D, which itself is controlled by a converter controller. And this converter controller tries to set the PV voltage. And this PV voltage reference value is generated by a MPP controller, or in case of a demand PowerPoint controller, in the case when we have requested power. Okay, in the following, I will start from the right to the left and give an overview about the components in the primary conversion. First of all, we have the electrical cell model for a PV cell. On the left-hand side in the circuit, we have a diode and resistors. We set this resistor RS to 0 just to obtain an explicit equation for the PV current in dependency of the PV voltage, which is given in this equation number 3. What we also need is the relation to disturbance like irradiation and temperature. Those both values affect the efficiency of the PV module, and the difference to the standard test conditions in S and in T can be taken into account by these equations. Some parameters are left, like AN and VT. These parameters are set, or we get this parameter by a curve fitting to the characteristic given by the manufacturers of the photocells. If we connect multiple photocells together, we get the PV module, and we can connect them in parallel or in series and add together the voltages and the currents corresponding. Okay, what are the characteristics looking like? If you see this on this slide, we have on the both left figures the dependency of the PV current and the PV voltage over the PV power over the PV voltage. And we see that for different irradiations, the generated power differs very much, which is not very surprisingly, but the point at where we can generate maximum power, the PV maximum power voltage, don't differ so much. If we want to generate less power, maybe if we only demand a part of the power we can generate at the current state, we can either go to the left or to the right of the maximum power point, and this can be controlled via the PV voltage, which we adjusted by the DC-DC converter I will explain in the next slide. On the right-hand side figure, we can see the dependency on the temperature, and here we see we have a dependency of the maximum voltage for the maximum power point and the maximum power as well. But as I mentioned before, the temperature dependency will be neglected in these slides. Okay, take a look at the DC-DC converter. In our case, it is a buck boost converter. As we can see on the right-hand figure, we can see it connects the PV voltage from the PV module to the DC voltage at the DC link. And this connection is controlled via the duty cycle, which controls the switch. For an average model, we can see the static relation between the DC voltage and the PV voltage in this figure. And we can see it is a nonlinear behavior, and we can, and at least in theory, we can reach every ratio between 0 and infinity. For dynamic analysis, we introduce two states. The first state is the PV voltage, and the second state is the current through the coil. This gives us the state vector, and the dynamic state equations can be seen here on the right-hand side, where we can see by this function f, which is again the PV current independency of the PV voltage, is a nonlinear function, so the system is nonlinear. And for further analysis, we linearize the system and take a look. So here we see on the left-hand side the linearized equations, and on the right-hand side we see the eigenvalues for different PV voltages. And what we can see is that for increasing voltages, the system behavior changes a lot. So let's say we pick one PV voltage as the operation point and linearize the system in this point and develop a controller for this point. We can't guarantee that this is a good controller for any other operation point. Therefore, we first start with a single linear controller, make a simulation, and then see that it's not a good performance, and then we will introduce a more advanced controller scheme. So the next slide is about the converter controller. In the first equation, we see a I-state space controller, which is a linear controller, and this is the starting point. Here we have the feedback of the states, and here we have the integral part. As I mentioned before, the simulation results were not that good, so we switch over to a DS controller, which is a blend of multiple linear controllers. The blend is controlled by these latent sum, and here we have the membership functions HI, which is itself controlled via the premise variables. Here we choose the premise variables to be the PV voltage, the irradiation, and the temperature of the cell. And in this table, you can see the operation points where we set the different linear models. Okay, on the next slide, I want to show you the simulation results for the converter controller. What was the experiment? The experiment was we have a reference PV voltage irradiation and cell temperature changing every 0.5 second stepwise. And what we show here is the measured PV voltage. So we see in the upper figure for the linear controller a not so good behavior in any case. In some cases, it may be good, but not in every case. This is especially then the case if we leave the operation point for which the controller was designed. In the bottom figure, we see the same for the TS controller, which is a nonlinear controller, and we see that performance is much better. So we stick to this controller and use this for our closed loop system. In the next step, we want to talk about the power point and how we can reach it, the maximum power point. First at all, the classic approach is to always fit in the maximum power that can be achieved. This is the maximum power point tracking algorithm, and here is, we picked one, the perturb and observation algorithm, which essentially works the following way. We perturb the system, so we change the PV voltage and then observe the reaction of the system. The reaction of the system is the produced power. And if the power is increasing, we keep on going the perturbation in the direction we already had done. If the power is decreasing, then we reverse the direction of the perturbation. So finally, when we reach the maximum power point, we will step around this point. And this is basically the algorithm which can be modified to increase the speed or the accuracy and also the robustness against changes of the irradiation, which means that the characteristic is changing. The slight modification can be done to get a demand power point tracking out of this just by replacing the feedback, which was former the PV power, by this difference. This is the PV power minus the requested power. And this means, what this means can be seen in the figure on the right-hand side. If we have enough irradiation to produce the requested power, which in this case is 0.6 PU, we got two maxima, which can be found by the algorithm. If we decrease the irradiation, then both maxima will come closer together until they met at one point, in this case for 600 watt per square meters. And if we decrease the irradiation more, then we still have a maxima, but it's not touching the zero, which means that we can't met the required power, but we still fed in the maximum power possible. Okay, that was the short introduction to the PV model we use. And now I give back to Horst to refer to the transfer functions of the RPPs.
Yes, thank you, Stephan. So back to the system view. So we have seen until now how we have modeled our two main devices, the PV and the wind system. And now come back to the link to the higher level. So we are able now to model our devices by a weighting combination of linear models. And based on this, we can describe this behavior, the full behavior based on physics and also on the control loop by transfer functions. And these transfer functions are important pieces and things to integrate this into the higher level DVPP controller. The higher level DVPP controller takes into account the behavior and the frequency. And we see here in this scheme of a typical grid, and see here the link and the transformer and the DVPP in this scenario. So we have also different other scenarios, but the simple scenario is that all these sub-devices feed or inject the power into one point of common coupling, and we can combine these three different devices in the frequency domain in such a way that this sum of all these transfer functions gives the desired behavior in this gray line. So this gray line is the sum of all the threes, and you see these transfer functions represent the dynamics of the closed loop behavior of the wind, of the PV, and the STATCOM battery. The link to our project is now that we are able to describe transfer function, the behavior of these local devices by transfer functions for different paths. You see here one important path is the path between the request power, which comes from the higher level, and the power which injected into the grid, into the point of common coupling. You see here 4 different types. Before we have considered 2 main systems, the PV and the wind. And we have also 2 other types considered, the solar thermal and the hydropower. So based on the closed loop systems before, we are able to derive a linear behavior, a linear model at different operating points. You see here this behavior at one operating point. Very important is that here you have a typically PT1 or first order delay dynamics of the solar thermal. You see here the wind turbine, which has this, it's actually the second operating strategy transfer function, which is here also a typical first order plus an extra dynamics, which comes here from the converter dynamics. And you see here the PV dynamics. So now we are able to use these models based on physics and control to take into account into a higher level controller. Here, some other ones. So the key result is that the operating strategy here of one wind turbine is similar to the dynamics of a wind farm. You see here the comparison between wind power plant dynamics with 2 power tracking operating strategies here. So yes, I switched. Yes, this is here. You see here the wind power plant dynamics with 2. The tracking operating, what Florian had mentioned before. We have 2 different strategies. We can change the power only by the generator torque, or we can change the power by both the power of the torque of the generator and the speed of the rotor. And what is important here is that the operating strategy based on the operating as the first has a much better dynamics in sense that we have here a higher bandwidth. So the bandpath frequency is here higher and drops later. So that's important. So we are here can follow the request of the power much better as the second strategy. And this both also the comparison between the grid forming and grid following converter. So based on this, and the third slide is here the comparison between single wind turbines and the wind farm. You see here that the wind farm is close to the behavior of the single wind turbines. So this gives us here the argumentation that it's possible to use an aggregated, we can aggregate a wind farm by a single turbine. See here based on this transfer function behavior. Now come to the conclusion. So we are able now to give you a hint and some results based on the questions before. So you have shown you the modeling of a primary conversion and secondary conversion with closed loops for PV and for also for the wind turbines. We have also integrated this the forming and following converter dynamics into our approach. And we have described here and show you suitable models which describe the dynamics of the RPPs, which can be integrated into the higher level controller. So first, we have models for simulation only. So if you are interested in simulation, you can use the models and integrate it in commercial software if you like. Or you can also use these models as a starting point for control-oriented design of DVPP, because here we have reduced models which fits to the DVPP approach. So that's it from my side. Now we have actually 12 minutes for discussion And I'm happy to see here if you are interested in some points and we can discuss it. Okay.
Thank you very much, Horst, Florian, and Stephan. Thank you for your for presenting to us the outcome of your research. And yes, we can move now to the question and answer session. So we already have 2 questions. I encourage the audience to formulate questions if they have some curiosity. Since we are glad to host the speakers, and they will answer live to your curiosity. So the first question regard the models that you use for the generator as a electromechanical system. So the audience is asking how have you modeled the generators and the electromechanical system that is behind it, and if you use MATLAB for the simulations. Thank you.
Yeah, thank you for the question. I want to answer it first very quick. So it depends, I would say. So when we modeled hydro, for example, the synchronous generator in a hydro power plant is directly connected to the electrical grid. Then we explicitly considered the electromechanical system, including the dampings from the windings and stuff like that. So we have an explicit modeling of the electromechanical system. However, in case of the wind turbine, where the back-to-back converter decouples the wind turbine from the electrical grid, we use the simple transfer function description for the synchronous generator, as we expect the back-to-back converter facing the wind turbine side is sufficiently fast, and actually the dynamics are there governed by the rotation of the wind turbine rather than the generator dynamics itself. And it is compared to the inertia of the wind turbine very small. Again, but for the hydro system, for example, we explicitly used I think 6th order model or something, or 7th order model for the synchronous generator to represent it. And yes, we use MATLAB for simulation purposes, but we try to keep everything in so-called S functions. And within those S functions, so we don't use, we use it in a Simulink environment, but the description of the entire dynamics are captured in those S functions, which allows us to give an explicit and analytical description of the derivatives, such that it can be pretty much used in any simulation environment that is capable of integrating. So whenever you have an integrator, you can simply use those models and then supply it there. Okay.
The second question is about models. So
yeah, so
open access.
Yeah, and then the second question: are the models open access or are there related publications? Yes, they are. First of all, there's a GitHub repository from the Positive project, and all the models discussed and even more we have uploaded them, so it can be accessed by anyone who's interested. They can be downloaded and used in simulation studies for themselves, or analyzed, or the control loops can be adjusted. So everything is free to use if you're interested. I think, is that
yeah,
true?
it is true, but we have not opened it until now because we have to.
Here's the last report.
We have okay. The last report is open access. Yeah.
The last report, I think, in GitHub.
Yeah.
Loaded it up.
I think it should be on the website of the Positive project.
Okay,
Yeah.
so it's yeah.
You will find it on the Positive project. If you have more detailed question, you can send us an email, and then we give you the link if you're interested in it.
Yes, and if the speakers agree, we can also include the links to the material, the publication, but also the GitHub repository in the description of the webinar that you will find in the YouTube channel. So,
okay.
So that the people can have all the webinar and also the references to it. Okay.
Yes.
Then we have another question. If you agree, we can move to the next one. In the last of the presentation, what I understood that the wind farm behavior could be seen as a single wind turbine, but it's easy to control a single wind turbine. However, if you see that you want the entire wind farm to operate on a certain point, how you will decide the operating point for each windmill? So this question, yeah, maybe if you can please elaborate this question regarding how to operate a plant that contains more than one windmill.
Yeah, it's related to wind farm control, right? So we have addressed this, but not here in this presentation, right? We have only shown.
Yeah, I mean, the main point there is, let's say at this point we neglect the active power losses in the wind farm grid. Then what we would see is actually the sum of all active powers of each wind turbine would be the sum, would be what the entire wind farm would given to the grid. And it really depends. Like I said, it's still subject to research. Some researchers argue that, for example, if the front row facing the wind of the wind turbines get derated more than the others behind, we can possibly balance the loads of the individual wind turbines within the farm, or even maybe increase the power output. This is something that is still discussed. The point there is, for this, you always need the information on the actual wind speed, where the observer comes in. So I would say for active power, it's pretty straightforward. Sum of each wind turbine's power is the power that is injected into the grid. However, for reactive power, it's quite different. There you need to consider the setup of the wind farm, more or less. So the electrical components that connect the individual wind turbines have an influence on the reactive power injected into the grid. There it's more, there you need to take into account really the structure of the wind farm. This is then more complex, but can be used. There, I think transfer function models for this wind farm can be generated and then used to dispatch the individual reactive power commands to the wind turbines. I hope this was, I answered the core of this question at this point. Yes.
Optimal maximum power point tracking for what? For PV, wind, for farm, for wind, or for PV. So that's because it's different.
I think, I mean, Stephan elaborated on PV, so I guess it means the wind turbine as well there. It follows this. We use the TS-based full state space controller, where we can also share a publication where we discussed how this is designed and implemented, which will be also in the links at the YouTube tutorial that we discussed. However, it follows the usual structure. So what we're trying is, in partial load region, we're trying to optimize the power output using the generator torque, while limiting the power produced by the wind turbine in the full load region using the pitch angle. But it is a full state space controller that uses the observer-based identification of the current effective wind speed. So yeah, we will give the link to this publication, and there it can be seen in detail. And if there are any questions, please feel free to also contact us via the contact details that are written there.
And for PV, we have used a standard.
Yeah.
Maximum power point, but we have also extended the standard for demanded power point tracking, because as I showed you on the last slide, we are able to follow request to power request. So we have to also change the power. So we do both for PV and also for wind turbines. So this is not a standard controller.
Yeah, this extended version of the
standard version. So
The top observation
of the put job and observation algorithm. Exactly.
Okay, thank you very much for your answer. I may pose the last question. Is there any experimental validation plan for the models that you are developing in the project?
Yes, we have planned this and we have built up a testbed system. Stephan can show the audience what is here in our university. We have built up a testbed system, and based on this test system, we are able to consider the effect of our models and the controller on the grid. So in the middle of the figures, you see here our transmission grid. On the right-hand side, here we have our back-to-back converter. We can implement the PV, emulate a PV or wind farm. And on the left-hand side, we have also machines. So we have here our synchron generator, which build up here our grid. So we can emulate different scenarios in the grid. And we have also a barrel-feeded induction generator. So based on this testbed system, in the next step, we test and validate our control concept.
Yeah, maybe I can add something. So the main idea there would be to implement the dynamic behavior of the individual models we have in those back-to-back converters. And then we can test a higher level DVPP scheme that individually commands the implementation of the different local RPP devices to be able to show that within a DVPP framework, we can coordinate the different sources in order to achieve the desired behavior of the entire entity of the combination of the different RPP devices. Yes.
Okay, nice. Thank you for your answer. But well, you haven't mentioned it, but your models are used in a kind of our hardware or power under in the loop simulation, or you don't need this kind of framework for simulating your models?
We always connect them to a very simple grid at this point. I mean, within the project, there are partners. They develop more elaborate grids, and we interconnect our local devices with those advanced grids. Yeah, but if you look at the GitHub, you will see every device is connected to a very simple grid that just emulates some behavior, but also has the possibility to perform frequency changes, voltage drops, and all that stuff is tested within there. And then our partners supply us more advanced grids, and then we connect them.
Okay, nice. So yeah, it's not strictly necessary for having this framework for hardware simulation. Yeah, okay. Thank you for your answer. Okay, it seems that there are no other questions from the audience. So on behalf of ISGAN, I wish to thank you, Horst, Florian, and Stephan for proposing and presenting your research activities in ISGAN. And I'm also thank you all the audience for joining the webinar, and also for the questions that you pose. And so maybe if you have a final sentence, please feel free to close the webinar.
Of course, thank you very much. So it was a pleasure for us to give you the current stage of our project, and thank you for the questions and this more discussion in our web seminar.
Thank you very much. Yes.
Okay,
Bye,
thank
guys.
you. Bye bye.
Thank you.